Good morning once again. Welcome to the session 4. Some participants are yet to join. But still we'll start our presentation. Let them join. So I'm giving sharing rights to you, sir.
Okay, sir. Sure.
Give me a couple of seconds.
All right, sir. I got it.
Is the tab available?
Sir, I got it.
Thank you. Thank you. You can start, sir.
Sure, sir. Yeah. All right. So now what we can see, we have done how to apply constraints for the pure combinational logic block. Let us move on to the next section, which is called as timing exceptions. So after this section, we will enter into the IP and platform designer, and then we'll understand on the Intel-SoC FPGAs. Right. So now we can see when we are trying to check in the earlier case, both the launch flip-flop and the capture flip-flop are having the same clock. We can also think of another case, like we have constrained everything in one clock period, in one clock cycle. But then that may not be the case in most of the designs. For example, we have to take more than one clock period to transfer the data from one flip-flop to another flip-flop. Then it is not called as a single cycle path. It is called as a multi-cycle path. Now, if we go through the logic here, a multi-cycle path is a path which takes more than one clock period to propagate the data from one flip-flop to another flip-flop. So now what happens really when we are trying to check the launch and capture? So that means we cannot do the same setup and hold relationship for those paths. Because what happens is like it takes more than one clock period. So now designer specifies number of clock cycles to move it. We have to provide whether that will work in one clock cycle or 2 or 3. So that means we are going to specify how many number of clock cycles are required to propagate the data from one flip-flop to another flip. Right. Now, how do we apply that? When you say we have to specify a multi-cycle path. For example, you could see we have the clock, which is clock. This is the launch clock. And then you can see clock 1, which is the capture clock. From the launch to capture, we are providing 2 clock periods. You can see that the value is 2. So it takes a 2 clock period to transfer the data from the clock to clock 1. It takes 2 clock periods to get the data. In that case, we cannot do the normal setup and hold analysis which we performed earlier. We have to provide the multi-cycle path exception in this specific design. Right. So this is not only for setup analysis, it has to be done for the hold analysis also. Right. Now let us take this example. Now we have the launch flip-flop is having a 50 megahertz clock, and the capturing flip-flop is having a 100 megahertz clock. Now you can see this is from 50 megahertz to 100 megahertz. And you can see this is from 100 megahertz to 50 megahertz. So which of them requires a multi-cycle path? When you say there are 2 designs. One is from 50 megahertz is the launch and 100 megahertz is the capture. And for the other one, 100 megahertz is the launch and then 50 megahertz is the capture. You could see the clock period logically here. Now you can see the 50 megahertz clock, right? And then you just check with 100 megahertz. It takes 2 clock periods, right, to launch the data and then capture it. For example, you are going to launch here, but you cannot capture here. Where you should capture? When you are launching here, you should capture here. In that case, if you see here for the 100 megahertz clock, it is not 1 clock period, it is 2 clock periods. So the design 1 is a multi-cycle path, because for the 50 megahertz clock, it requires 2 clock periods. That's what we should understand. It requires 2 clock periods. So we require a multi-cycle path of 2 clock periods for the setup analysis and 1 clock period for the hold analysis. Because for the hold analysis, we are going to do n-1 because it has to be done in the launch clock only. So that is only 1 clock period. There is no change in the hold analysis. But for setup analysis, we should provide 2 clock periods. So this is very, very important for us. Okay, how this is going to help us in timing analysis, that we will identify right now. I will provide a demo and I will share the lab manual with you so that you can also practice that. Okay, what is the basic scenario? Let us understand that right now. When we go through the timing analysis materials in the lab manual, you have a multi-cycle path.qr. This is the first one which we did. And you can see multi-cycle path.qr, which is the Quartus archive file. So just copy that. And we go to the C drive and we'll create a new folder, which is called as multi-cycle path, or just to say multi-cycle. Inside this multi-cycle, you paste that Quartus archive. Okay. Now we can come back to the Quartus Prime design software, and then you close this design, close project. You can save the constraints file if you want. Now what we have to do is like click open project, and in the C drive we already kept multi-cycle, so we can open that multi-cycle path design now. So inside the multi-cycle you have multi-cycle path dot QAR, the Quartus archive. Okay, now you can see the multi-cycle path.v. This is the very lab. Okay, what is the need for understanding this? When you say here, you can see there are 2 clocks. One is always at passage of clock 333 megahertz. That means you have a clock of 333. And then you can also see always at passage of clock 666. It means you have 2 clocks here. One is 333, other one is 666 megahertz. But then what you could see here is, what is the data that is transferred from 333 that has to be captured in 666 megahertz clock, like the 50 and 100 megahertz clock which I showed you earlier. It is exactly same case here. But what is the problem when you say we are expecting this to work in 1 clock period? When we are expecting this to work in 1 clock period, then definitely there would be a violation, because here you can see that it requires 2 clock periods to transfer the data from one flip-flop to another flip-flop. But what we are trying to do is we wanted that to work in the same clock cycle. What is there in reg sum need to be taken to the sum of this clock. So it is possible when you say, then definitely we'll have issues in the timing analysis. Okay, let us open the SDC file. When we go through the SDC file, there are 2 clocks. One is create clock, one is 333 megahertz. Other one is create clock, which is 666 megahertz. But there are 2 clocks, but then there is any multi-cycle path that has been applied when you say that has not been applied. That means we didn't specify that it will take 2 clock periods to transfer the data from one flip-flop to another flip-flop. So that is not specified. Then what will happen? Let us understand that right now. You can directly copy the multi-cycle path QR file, which I'm going to share it with you, and then you can directly create the design. That means you can just open the design. We will perform compilation. Let us compile the design right now. Okay, now if you see that we have completed this 100%, but then we need to open the timing analysis and see what is happening inside the design. So now you can go to the tools and then go to the timing analyzer and then say create timing netlist and then here we can see report clocks. So that how many clocks are there, we will come to know. There are two clocks here. One is the 333 megahertz clock. Other one is 666 megahertz. Both are available here. Okay. Now, is there any problem in the timing analysis? That is also very important for us, because first we should understand, is there any problem of violation? Then only we can fix it. So now we can go to report timing here, say setup, and say report. You can see there is a violation, because what we are expecting that to work is like, if you see the waveform very carefully, launch is here, and then capture should happen here, because this is the completion of one clock period. But what we are trying to do is, you launch here and then you capture here. We are doing. That means this is only half cycle, not one clock period. Then what happens is, the tool is trying to capture it. That means it will get violated because we cannot get the correct data. Now what happens here is, like, this is launch and this should be the capture. If this is the capture, then it is not one clock period. For this, it requires two clock periods to propagate the data from one flip-flop to another. So now from clock 333 to clock 666, you can see that slack is violated, because the required time is only 4.8, but the arrival time is 5.4. 4.8 minus 5.4, if you see, it is showing a negative slack. And you can see there is a launch clock is 333 and then latch clock is 666, and they are not of the same. There are two different clocks now. Okay, so can we check the hold analysis? When you say yes, we can try that also. Report timing, go to hold, and then we can click the hold analysis. In the hold analysis, it is arrival time minus required time. So then it shows positive slack. But then since there is a problem with the setup analysis, we have to ensure that the problem should be solved. Okay, how are we going to solve this problem? When we say we need to apply a multi-cycle path constraint for the design. Okay, how do we do that? When you say, help you out, there is a lab manual, which I will share it with you. I will show that you, so that you can directly follow the steps here. If you open the design files lab manual, there is a timing lab. Here, all the examples, like starting from the first two, I have already explained to you. Without going through the lab manual, you can try that later. Now you can see lab 3, which is the multi-cycle path example, which I need to show you here, because this will provide an idea like how you can go through step by step. Like, you can see that I have showed you both clocks here, clock 333 megahertz and the clock 666 megahertz. Both are there, but we need to apply a multi-cycle path constraint. This is what is very important for us. Why we need to apply? Because the clock 1 is running twice as fast as the clock. So we need to wait for 2 clock cycles before activating the data. Because of that, we need to apply this multi-cycle path constraint. Okay, is there any constraint already applied or not? How do we know that? When you say, one is you can open the SDC file. Other one is you can see from the tool itself. See, for example, here there is a tab called report exceptions. When I click that, and then if I say report exception, it shows that no exceptions were found. Please note that an exception is one of the false path, multi-cycle path, at min delay or max delay. So there is no min delay, there is no max delay, there is no multi-cycle path, there is no false path. None of them is provided inside the constraint. Therefore, the compiler is not in a position to find out and provide you the timing exceptions. Okay, how do we apply that right now? Then we can say that that's what is provided here. Okay, in the lab manual. So follow the same steps. Right, now how I can do that? We can open the constraints and say set multi-cycle path. So constraints, set multi-cycle path. Here you can see from to. To means it is going through what kind of lookup tables, ALMs, that information you can provide through the net. If not, you can directly give from and to. So if I say here from, I can say list. There are 2 clocks. So I can just click here from 333 megahertz clock. Okay. Then I should say 2. Then I can click here, list, and say 666 megahertz clock. I should provide. So from get clocks 333 to get clock 666 and say value 2. 2 means 2 clock periods. It is not 2 nanoseconds. Don't get confused. Okay. Here 2 means it is taking 2 clock cycles. Okay. What is your clock period? Multiplied by 2. So now you can say that. So set multi-cycle path from get clocks 330 to get clocks 666. Set -n2 is there. It's done now. Now, what is the next step you're supposed to do? We say apply the multi-cycle path logic for the hold analysis. So go to constraints, set multi-cycle path from say list 133. Okay. Then to get clocks list 666. Okay. Then you can click hold and say 1 clock. Now you say that. Now I apply 2 commands. Set multi-cycle path from get clocks and set multi-cycle path from hold. Both are provided. Now what we are supposed to do when you say after applying these constraints, we have to check whether the design is meeting timing or not. Just give report timing and say report time. Now you can see it shows multi-cycle path which is 2 clock period. Right, and then it shows that this is the launch and this is the latch. You can see that between the launch and the capture, you can see there are 2 clock periods. That's what we apply. We applied a multi-cycle path of 2 clock periods so that 1.5 became 3 here. So that from the clock 333 megahertz to 666 megahertz, we have a relationship of 3 nanoseconds, so it is meeting time. So the required time is 6.329 now, and the arrival time is 5.467, so the design is meeting time. And the same could also be for the hold analysis. So click hold and then check. You can see that. Because there is no problem with hold analysis because we are going to do that in the launch edge only. So that is only 1 clock period. But then for setup, you can see we have to do it for 2 clock periods. What is the understanding here is like we have to ensure that the multi-cycle path constraints need to be applied for the design in order to complete. Otherwise, what will happen is you may require 2 clock periods, but then you are asking the design to work in 1 clock period. Then the design is not properly constrained. So your design has to be properly constrained. Only then we can enter into the next step. In the lab manual, the step-by-step process is provided, and you don't require any hardware for this particular lab because this is completely on the timing analysis. So you can use this lab manual and complete all the 3 labs which is provided. The first 2 labs are just a project setup and then how to use the timing analyzer, which I explained to you already. And this is the multi-cycle path example, which has 2 clocks. Okay, and the lab manual has the steps and the lab file, the Quartus archive file. I will share it with you. You can directly open the Quartus archive file and then you can check that and then complete the lab also. Right. Now, this is the logic behind the multi-cycle paths. There is one more which we need to discuss is called as the false path before we enter into the IP and the platform design. Now, if you see here, the another important timing exception is called as the false path. So what is a false path? That is very, very important for us to understand. So false paths are paths, right, which are not, that means you can see how exactly it is explained to you right now. So paths in a design that physically exist, but will never be exercised by the circuit. That means it won't be exercised by any of the test vectors. So we are not exercising that. That path is not getting exercised by any of the test vectors when you say, then that would be a false path in the design. So how a false path will look like, that we need to understand. These paths have no functional purpose and they do not need to be constrained. They need to be ignored during timing analysis. So specifying a false path removes it from timing analysis. The timing analyzer tool will ignore the false path. Okay. Why false path need to be ignored, and then what is the problem with the false path when you say? Let us explore one simple example here. Let us take this example. Now, what is the dangerousness? Let us understand that here. Because the STA does not require any test vectors. For the STA tool, it will just see which are the input logic, like it means which are the start points and which are the end points, and to find out how many number of timing paths are. If you take this case, there's a path from A, C, C1, C2 out. There is a path here A, C out. B, B1, B2, C, C1, C2 out. B, B1, B2, C out. There are 4 timing paths you could see. But then there is one select line that is connected to both multiplexers. Even though there are 4 timing paths, only 2 are valid based on the select line. If select line is 1, then A, C, C1, C2 out will be valid. If the select line is 0, then B, B1, B2, C out is valid. What are the other paths when you say A, C out? B, B1, B2, C, C1, C2 out. They will never get exercised by any of the test vectors. Even if you pass 0, they will never get exercised. Even if you pass 1, they will never get exercised. But what is the dangerousness here? When you say if the timing engine tool identifies that B, B1, B2, C, C1, C2 is the longest path, and we apply timing constraints for it and then find out that to solve that you are applying constraints in such a way that, okay, that path is meeting timing. What is the use? Because that path need to be ignored during timing, because that path will never go into happen. So this is the dangerous. So the STA does not require any test vectors, but then it is the designer's responsibility to find out what may be the false paths of the design. So you have to be very, very careful. So by applying this constraint, what happens is the timing analyzer will ignore those 2 paths and then it will activate only the other 2 paths. You can apply set false path or rest of this so that they will be ignored during timing analysis. That means the compiler won't calculate the slack for the false path. The slack for the false path is infinity. So it is not going to calculate for us. It will be ignored during time. Right. So there are 2 more slides which I need to explain to you. One is we were discussing about what is the problem with delay, like clock latency. So that is very, very important for us to understand, because even though the clock starts from the clock source, it takes some time to reach the flip-flop. So we divide them into 2. One is called as network latency. The other one is called as source latency. Source latency means delay between the clock definition and its source. That means from the clock definition point, right, from the source to the clock definition point, you should see. And then what is the network latency when you say between the clock definition and then to the register clock pin? How long it takes to reach the register? So we call this as a network latency. Source latency plus network latency, both would be taken as the latency. So clock latency, if they say, it is a combination of both network and the source latency. Another thing which we need to understand is called uncertainty. So this also, while explaining the concept, I gave the idea, but then you may not have clear picture on what is happening. Now you will get a clear picture. First thing is, one is called skew. The difference in arrival of the clock between 2 successive registers I explained. So it is known as clock skew. And the other one is deviations from the exact defined period. That means frequency variations in the clock source is called as jitter. So because of this, like due to aging of the crystal oscillators or due to noise, whatever may be the voltage fluctuations, variations, temperature variations, you may get jitter. That means it won't be happening in the consecutive clock cycles. for example, in 10,000 clock cycles or 1 million clock cycle, the clock edge may be shrinked or it may be elongated. That's what we call that as a jitter. So we call that as uncertainty, and that uncertainty need to be removed, right, when you are calculating the timing analysis. Right. Then what is very important for us to understand is, while performing the timing analysis, in one place we are taking the minimum value, in another place we are taking the maximum value. Even though they are having the same buffer, but then they may not have the same delay component, because for one particular analysis we use minimum, for other one we use maximum. Even though it is the same clock path, for one analysis we take the minimum value, for another analysis we take the maximum value. So this is called as clock pessimism. Okay, that is also very important for us to note down. Right, so now we are in the last step to understand. If my design is having setup violations, how do I solve the problem? If the design is having hold violations, how do we sort out the issue? That's what we need to understand here. So these two steps are very important for us. How do we achieve faster timing closure? So whenever setup violation occurs, means a setup violation occurs when the data arrives too late compared to the destination register's clock speed. How this will happen? As I mentioned earlier, there is a launch flip-flop, and then there are so many combinational logic levels, and it has to reach the destination register. Before the data reaches the destination register, there are chances that the clock will reach. So what we are trying to do in that case, we need to divide the combinational logic block. That means we need to divide. That means we should insert a flip-flop into the combo logic. That's what we are trying to do, that as a pipeline. Okay, so now what we need to do, what are the steps available? Tell fitter to try harder. That means you can tell the fitter, that is placement and routing tool, to apply some optimization techniques. That is one. Second thing is rewrite the code to remove the logic states. Okay, instead of applying that, we can rewrite the code. Third one is adding pipeline. That means we can insert the registers into the data path. Fourth one is called slow down the clock. You can see in brackets undesirable, because this is the one which we try to do manually in the first example. The design was not working at 20 nanoseconds, so we changed that to 21. So that is not the best method. It is not the desirable method. It is an undesirable method. So fixing the setup violation is very challenging, and we have to follow these methods to fix the setup violations. And how do we fix the hold violations here? So fixing the hold violations, when you say, it occurs when the fast data and clock register has latency now. That means you need to insert the buffers into the data path. So when you are inserting buffers into the data path, we should be very careful, because if you insert more buffers, that will affect setup. So Quartus will attempt to fix automatically by adding delay in the data path, but we should be very, very careful. On some occasions, fixing hold breaks the setup. So when you are fixing the hold, that should not affect setup time. We should be very, very careful with that. And then finally, the summary, if you see, don't take timing analysis for granted. So what they say from that, when you say it is very expensive if not dealt with the design stage. You could see that in multiple cases we have taken the case studies to show that how multi-cycle path need to be fixed and how false path need to be fixed and how we need to apply different timing constraints for the design. Everything we have seen that. And we have to understand the scenarios, and we have to think about our constraints. And we have to understand the digital electronics timing fundamentals. So it is easy for us to design reliable FPGAs. Because if you know how the tool performs the timing analysis, then it is very easy for us to design, and then we can understand that process and continue the steps. Okay, so to revisit what we have seen, if the first section is done, now we have seen how to apply timing constraints we have done, and then let us move on to this, like understand the basics of IP catalog and IP design and platform designer and introduction to Intel-SoC FPGAs. I will show that to you with quick demos and get understanding of it so that we can get detailed picture on SoC design tomorrow. Right, let us go through that right now. I will close all the design, and then we open the Quartus Prime design software again to work with IP catalog. Let us enter into the intellectual property, which is called as the IP catalog. We call this as FPGA IP course when you say. What is an intellectual property? That's what we should understand right now. The complex functions that Intel designs for our customers, so they don't have to design it themselves. That means IPs are pre-designed, they are pre-tested, and they are pre-verified. They are designed, they are tested, and they are pre-verified. That's what is already available. It is like on the shelf, you can get it, and then you can reuse it. Sometimes IP is free. That means you don't need to worry about it. It is already available, like free. And the more complex stuff cost, it is expensive to develop and make sure it works. The main problem is like, see, somebody is providing you the IP. What is the guarantee that it works very well? Okay, if the IP does not work, to whom to report? These kind of questions are always there. So somebody is providing you the IP. For example, you wanted to design a floating point multiplier. We don't know how to write the Verilog code or VHDL code of a floating point multiplier. Somebody is having that floating point multiplier, and they are informing that, okay, I have that floating point multiplier which will effectively work. So you are buying it from the third party, and then you try to integrate that in your system. Because of the floating point multiplier, we are not able to achieve the target. That means there is a bug in the floating point multiplier. So how will you proceed then? You purchased it. You have that floating point multiplier with you in the design. And because of that bug, you are not able to proceed to the next step. So we have to be very, very careful. These are some challenging things which are happening in the IP world. So what are the examples of IP when you say Ethernet controller, PCI Express controller, and then you have a soft processor, and then multiplier functions. All those things will come under the intellectual property, which is the IP code. Right, now let us explore those IP codes. What are available? From where we can get the IP codes? So that is present in the IP catalog, which is available in the Quartus Prime design form. And what are the things that are available in the IP course when you say basic functions, bridges and adapters, DSP functions, Intel FPGA interconnect, interface protocols, low power functions, memory interfaces and controllers, processors and peripherals. All are available there inside the IP catalog. How it will look like? Let us explore that one simple example here, right? When you open the Quartus Prime design software, we can analyze and check, okay, where is the intellectual property. Let me just open and show it. On the right hand side, you could see that IP catalog. And then you can choose the device family here. For example, I expand this and show for max 10 devices. What are the important things that need to be considered when you say? In the earlier case, like when we were discussing about the DE10 Lite, this is having only the soft core processor. Whereas when it is the Cyclone 5 SoC, I opened the DE1 SoC lab manual yesterday and showed you there is an FPGA as well as there is a processor. Both are embedded inside the same fabric. So in that case, there should be a processor which is already available, right? How do we check that when you say, we have selected max 10 here. And when I expand the processor here, right, you could see only NIOS is there, because NIOS is the soft core processor which is present inside the FPGA fabric. Thus, instead of selecting the max 10 device here, I select the Cyclone 5 device. And then I expand the processor and the peripheral. You can see that hard processor component. Right on that, so you could see there is a hard processor component that is available in the. So along with your soft core processor, you can also see that there is a hard core processor that is available with the Cyclone 5. It was not available in our earlier device. So this is very, very important for us to understand. So what device and then what kind of intellectual property cores are available? That is very, very important for us to understand. Okay? Otherwise, it is very tough for us to analyze and understand that what are the IP cores that could be supported by that device. Okay, right. How do we get more details, right? So that I can just show it to you right now. For example, I say here, you can directly go to Intel.com website. Okay. When you go to the home page here, you can go to the products. Here you can see there are multiple products available. But what we wanted here is the Intel FPGAs or Intel SoC FPGAs. For example, I just click here Intel FPGAs. You can see that all the FPGAs that are available. Here you can see Cyclone series. And then you can see the Cyclone 5 FPGAs and the SoC FPGAs. Because you can see this is a system on a chip SoC FPGA. Whereas in the Max series, if you open, right, so they can see Intel Max 10 FPGAs, but then they are not a family of SoC, right? They have only the soft core processor. Like, what is this soft core processor and what is this hard core processor? That's what we should understand right now. To understand that with clear picture, you can directly refer to the same, right? In our home page itself, you will be getting a clear picture on what is the basic idea of the SoC FPGA. That's what I'm going to show you so that it is easy for you to grab the information and then get a clear picture. Okay. If you are very new to the world of FPGAs, you can download this free ebook, which is available in our homepage, FPGAs for Dummies. Okay, you can get this detail. This has all the information like what is present inside the FPGA, synthesis process, implementation, what happens inside that algorithm, all the direct informations are available. You can download this FPGAs for Dummies book if you require. And then what I wanted to show you is the SoC FPGA. What is an FPGA? This is what we discussed in detail yesterday. And today our focus is on what is an SoC FPGA. Right. So now when you say what is an SoC FPGA, when you say even we need to have more discussion on that, but then at least we'll understand the definition. SoC FPGA devices integrate both processor and FPGA architectures into a single device. You could see that it has the processor as well as it has the FPGA. Both are present into the single device. That's what we call that as an SoC FPGA. How do we integrate them when you say? Integrating the high-level management functionality of these processors, and then you can see there are some real-time operations that could be done by that. So how that could be possible? Let us understand that here. Okay. So what is the advantage of having both processor and FPGA in a single device? That's what your question may be. If I wanted to integrate both processor and FPGA in a single device, what advantages we are getting? Say they provide high integration, that is higher integration, lower power, smaller board size, and higher bandwidth communication between the processor and the FPGA. What is the need for an SoC FPGA when you say, why do you want to have both processor and FPGA in a single device? When you say, when both processor and FPGA are present in a single device, then you are able to get higher integration, lower power, smaller board size, higher bandwidth, all those things we are able to get it. Okay. Along with that, what another advantage we get when you say they also include a rich set of peripherals, on-chip memory, everything, and then you also get a high-speed transceivers. Everything is available. Okay, this is the first question which we need to understand. Now, what is the next question that need to be answered before we enter into the basic labs? When you say, what kind of processors are available in FPGAs? So this is very important for us to understand. Because I'm going to show you two demos. One is with the Max 10 device, where we are going to use the Nias 2 processor. And the other one is with the Cyclone 5 device, where we can try to use that with the Cyclone 5 device. That means we can use the hard processor system. So both demos you can do with the light version, what is available here, with the help of the platform design. So how do we do that? I will show that. Before that, let us understand the basic concept here. Processors in SoC FPGAs can be hard or soft. So now when I say SoC FPGA, then inside that the processor can be a soft processor or it can be a hard processor. Right? What is a soft core when you say? The soft core is the NIAS2, which is available in the FPGA. They are implemented in the programmable logic. That means they are going to use the FPGA resources. So a soft processor is one which is going to use the FPGA resources. It is going to use the adaptive logic modules, the memory resources, and the DSP resources which are present inside the FPGA. So using the FPGA resources, if you are building a processor, that is called as the soft core, which is the NIAS2, which is present inside the FPGA fabric. Okay, then what is hard when you say? The hard processors are implemented in the fixed silicon logic of the SoC FPGA, similar to the transceivers. Like transceivers, they are third-party processors. That means we are immersing a dual-core ARM Cortex A9 inside the FPGA fabric. On SoC FPGAs, right, they are having the hardcore. That means you have the processor, along with that you have the FPGA. Right now, the Max-10 device, which we got explained yesterday, is going to have only the soft core. And we call that as a soft core based embedded system design. Whereas when we are trying to use Cyclone 5 and then we use the hard processor system HPS, then we are going to generate a hard processor based embedded system design. So we can try to do that. How to approach the basic lab, that we will understand. So there are 3-4 demos I can show you. You can also try that. Not a big deal. It's not very tough that you can easily observe that. But anyway, I will share the lab manual with you so that you can definitely practice. For these labs also, you don't require any hardware because we are going to generate the HDL and then bring the portion. We don't want to implement the design onto the board. We are understanding how to perform integration rather than implementation. Okay, let us understand. So now you know what is an SoC FPGA. I will explain in detail later. But what kind of processors are available in FPGA? So these two questions are answered. Now let us enter into the IP catalog and we will try to do a simple lab with that, and then we get an idea of what is a platform design. Okay. So if you go through the intellectual property here, for example, I select here Max-10. Okay. Now what we are supposed to do here, for example, we say that I wanted to create a new project wizard. You can create new project wizard and then we can bring the intellectual property from here. Okay, so you can bring the logic from the intellectual property. Let us identify one now. For example, I type here on-chip memory. You can see that yesterday, when I was explaining about the memory resources, I told you that the memory can be configured as a single port RAM or a true dual port RAM or a simple dual port RAM. And also they can configure as a ROM. All those things I explained. And then it can be configured as a FIFO. Now if I click here RAM one port, that means RAM single port. It's a single port memory. When I double click that, it is asking me where I can store this. Like you can see that it is getting stored into the installation directory. So if you don't want that, you can try to do that, okay, after creating the project. So we can also try that. I will show that to you. New project is that, and say like next, and then you can see here a drive and say IP design. Okay, and then you can say mem. Right now you can see that next. Do you want to create it? You can say create empty project. Nothing required. So now you can see here, you want to select corresponding devices, you can select. Select the device, say next, and then finish. Okay. Now what you can do is, here you can type now, on chip memory. Okay. Now you can say RAM single port. Then you can say mem. Okay. Now you can see that this is called as the Mega Wizard. This Mega Wizard plugin manager will show you about what are the parameters you can enter to integrate this intellectual property to your design. So let us take this RAM single port here. You can see that what are the parameters that are available one by one. We can try it right now. If you see here, what is the scenario? You have data 7 down to 0, and then write enable, address, clock, everything is available. Now it shows that do you want a single clock or you want a dual clock, which is you can use separate input and output clocks, whichever you want. Okay, but when it's a single port RAM, I can have a single clock, not a big deal. But what are the options which we can try here? You can see that. You can see auto, MLab, M9K, M144, and then LCC. You should know that what is this MLab. So you have MLab. That means called as memory lab. What is that memory lab? You can recollect in the yesterday's discussion. We have adaptive logic module, ALM, which has 8 input lookup tables, 2 3 input adders, and then registers, right? 10 such ALMs are combined together to form the logic array block, LAB. Using those logic array blocks, if you are building a memory, that is called as MLab. So MLab means it is a memory logic array block. A memory logic array block is one which is built using the logic array block. Right? I don't want that when you say it's like a distributed memory. I want a block memory when you say, then you can take that M9K. This is a block RAM which is already available. You can select whichever you want. If you keep auto, then the tool will select right from its own, like by seeing the architecture. So you can see how wide you are telling that 8 bits and then 256 words you want. If you want to change it, you can change it. Otherwise, you can keep it here. But what are the other options we wanted to try here? To say next here. Here, if you wanted the queue to be registered, that means you can write assign statement or you can write always, right? And then you can register it. If you wanted to register it, you can say that yes, I want it to register. But you can see the difference. If you say yes, register, you can see this output comes here and then it goes to your flip-flop and then goes to the queue output. If that is not the case, you can see that is required. Okay, this is your wish. Whichever you want, you can try that. And then if you wanted to add any clock enabled signal or asynchronous clear or read enabled signal, anything in your design, then you can enable this information here. Now say next. This is very important for you. If you are writing the data and then you wanted to read in the same location, so in that case, you will always have a problem. There is a read-write collision. To avoid that, whether you wanted to have the new data or you wanted to have the old data, or whether you should say don't care. So that information is provided here. By default, it will be new data, but if you wanted to modify it, yes, you can. Now you can say next. Okay, there are two options here. In the first demo, I'm not going to show you how to create the memory initialization file. Later, I will show you. Now, if you see that, you want to specify the initial content of the memory. That means if you wanted to provide the memory with some initial values, yes, you can provide that initial content with a memory initialization file. If you don't want, you can say no, leave it blank. At this junction, let us leave it blank. Later, I will show you how to create the memory initialization file. say next here, right? And then you say generate netlist, and then say next. If you wanted to see the instantiation template file, you can include that also. Now say finish. Now you could see the design is adding a 2IP file, which is the Quartus intellectual property file that is added. Say yes. That you can see the file which is added. If you go to the files here, you can see there is a memory.quartus intellectual property file that is available. If you open that, you can see that information and then you can see the file here. See that? We didn't write the code. The code is already available. Whatever information you provided, input, output, all this information is already. So this is the intellectual property. Can we synthesize this when you say yes, you can. So we can perform analysis and elaboration, and then you want to compile, you can compile it. So we can try the compilation. So what was our focus yesterday is to develop the Verilog. And then the another way what I showed you yesterday was you can use the template, insert templates. But today our focus is not that. I need to directly take the IP which is already available. Okay. So you can take that block the IP, from the IP catalog, and then you can synthesize the design. So now you can see the schematic. Yes, you can see the schematic here. See, for example, RTL Weaver. You can see there is a memory. And you can also see the technology map weaver after the mapping. See that? This is a block RAM. The same code, the same thing has been generated yesterday when we copied the template. So you can generate in any method. Either you can develop the Verilog code, or you can take the template, or you can take the IP. So this is the RAM block RAM. Okay, where is this block RAM? You can see that block RAM in the chip planner also. For example, if you go to the logic, right, you can see like how exactly we can see that. So take the chip planner from here. So this is the block RAM. Right. So now what we have done, it's like we have analyzed how to generate the IP and then integrate your design. But what is very important for us is to initialize the memory content. Because when we need to initialize the memory content, we also need to add that memory initialization file. It was showing that you add the MIF file. Otherwise, it will be blank, right? So how do we solve this problem? When you say we can definitely create a memory initialization file. How do we do that process? Let us try it. Okay, so first you can close this project. You are opening a project, or you are creating a new project. There, how we can try this logic. Okay, so that we will try. Create a new project wizard, and then say here, create a C drive, and say like IP for design, something like that. You take and say memory, something like that. You create. Let it be some family. For example, you take Max 10. Now you can see file, new, and then here you can see that memory initialization file, which is called as MIF. So don't teach Verilog, VHDL or system Verilog. Click here, memory initialization. When you click memory initialization file, what it is showing is what is the number of words and what is the number of word size. You can just say OK. And then what we can do here is like you can custom the cells, like so it is showing with 0 value. But we don't want, what we can do here is like you can click here and say custom fill cells. Remember, open the memory initialization file and say custom fill cells. So here you could see in the custom fill cells, starting address is 0 and then you say ending address is 255, something like that. And here you can say incrementing or decrementing. So starting value 0, increment by 1, something like that. Whatever you want, you can prove. Right, and save it. Now you can see that it is storing the data till 255. So you have the memory initialization file. What we can do right now is like we can save this file. So file save as and say that memory.mif file. So this is present inside the IP design. You can save this file. And now when we are creating the project, right? When you are creating the RAM single port, so that time we can provide that logic here. For example, I say here on chip memory. You can
Padmanaban.
Yes, sir.
Yeah. Instead of say ascending or descending, can we also initialize it with the numbers which we want?
Yeah, definitely. It is possible. So this is like a custom fill, right? You can provide whatever details you want. You can provide a repeating sequence numbers also.
Instead of repeating sequence, you can have your own sequence also.
Yes,
okay.
Definitely.
Thank you.
This will help you to autofill because your memory size may be large, right? If it is a very small and you wanted to custom fill, yes, you can, right? But if it is like a larger thing and you wanted to verify, it is easy to use this process. Is that fine, sir?
Yes, you can proceed. Yeah. Because why I was asking is basically that if say we have to do say ECG signal processing or EEG signal processing, so if we can load that one complete cycle,
right,
then we can read from that memory.
Definitely, sir. It is possible. Yeah.
Yes. Thank
and there is a memory content editor which will help you to read those values also.
Yes. Thank you.
Yeah. So now, for example, if you open this, now what you can do in the earlier steps, what we did is like I will continue the same steps here. Right? If I don't want, I can remove registration, everything. So what was the basic thing what we left out last time is we give no leave it blank. But then what we can do right now while creating the intellectual property is yes, use this file, you can say. Then you can browse that and find out where is that file. For example, if you say all files, you can see there is a memory.mif file. You can open and add that file. Whatever content is there, that would be taken it out. So this is also possible for us. Either you can create it with the no, right, and then say leave it blank, or we can custom fill cells and that also can be added with IP file. So this is also very, very important for us to understand. Till all these things, what we were doing is like we were trying to do this design with the block level. But then can we do that at the system level? Like means we wanted to create multiple blocks and then I should generate when you say, yes, that is possible. And for that, we use a tool called as Platform Designer, which is already integrated with the Quartus Prime Design software. First, we'll understand that. And then I will show you two quick demos, one with the NIAS 2 soft core processor and the other one with the hard core processor, HPS. But then we will deal HPS in detail later, but then we will get an idea of like how that works out. Okay. So let me close this. Now let us enter into the platform design. What is that? Let us understand. is our objective for day 2, right? So, system design NP with platform designer. This is what we should do. What is the advantage of platform designer when you say? It simplifies the complex system development. It raises the level of design abstraction. It provides a standard platform because it provides you IP integration, custom IP authoring, IP verification, etc. It also enables design reuse, and it scales easily to meet the need of the end product. What is the advantage of this platform designer? It reduces time to market. It reduces design development time because all the IP cores are already available, where we are going to just integrate them and complete the flow. Right? What is the logic? How it does it? Just understand the concept here. What exactly is the platform? Now, when we say in components, you will have different set of interfaces. You could see there are masters, and then there are slaves available, and then there are different bus pages that are available. And now we need to integrate them. So it is very tough for us to integrate the design blocks and intellectual property. So integrating the design blocks and intellectual property is always tedious and error. How are we going to solve that when you say? That could be solved by the platform designer. The platform designer automatically generates the interconnect and it avoids error-prone integration. It saves development time with automatic logic and HDL generation because it enables you to focus on value-add blocks, and the platform designer improves productivity by automatically generating the system interconnect logic. How this could be possible? Let us explore that. Okay, how platform designer helps the logic here. So again, for this, I'll just show you a demo where you can also type it. So it's like we are not going to write any Verilog code so that we can easily try that. Okay. What we can do right now is like you can create a new project Israr and say in the C drive, we could create an example called platform designer. Say 1, something like that. Okay. What is the name of the project? Because we are not going to understand like what is present at this junction. So just say top. We can include whatever components we want. Then you say next. You create it and say empty project and follow the same steps like how we create. And the first we will do with Max 10 with the NIAS 2 processor. Later we will do with HP. So for example, you can see here 10M50 AF484C70. Now we have done this. Say next. Say next here and then say finish. Okay. If it is Quartus Prime design software logic, like generally what we will do is like we will enter into file new and then we will open the Verilog code or VHDL or system Verilog and then start typing, right? That is not the case here because we need to integrate and then you need to create a system. So how do we do that here? What are the options you know earlier? Tools, run simulation tool, until simulation. You are aware. Tools, timing analyzer. You are aware. Tools, netlist viewers. You are aware. Tools, you are aware. Now, what we need to know when you say in the tools, you can see there is a platform design. Okay, so you have to click platform designer, which is like a system integration tool, which helps you to generate the system. Okay, so this is a system integrator tool, which is useful for us now. Now you can maximize this. Now, in the intellectual property, right, in the Quartus Prime design software, the IP catalog was present on the right hand side. In the platform designer tool, you can see the same components are available on the left hand side. You can get the IP here. You can see there is a top level signal clock and reset. With the clock and reset, we can connect all the other components whichever we require and then create a system. Okay. Now, for example, since it is like a design where we use the Max 10 device, right? And then I wanted to use a soft core processor. I can type here NIAS, which is a soft core processor. You can see that the NIAS 2 processor is there. You can double click that. Here, NIAS 2 processor is available in two variants. One is economy variant, other one is the fast variant. Okay, we'll go ahead with the economy variant because fast variant has so many number of other options that could be available, but there are some licensing that is required. We'll go ahead with the economy variant. Okay, it's safe. Now you can see there are multiple errors that has been generated from the tool. What are these errors when we look into it? You can see NIAS 2, right, also has a clock input. Processor, right? Because it's a processor, it has a clock. That clock needs to be connected to the top level clock. When we write the Verilog code, what we will do, dot clock is connected to clock, we will write, and dot reset is connected to reset, like that we will write now. Similarly, we have to connect this. So that is very, very important for us to connect. You can see the instruction cache is larger than the instruction address. Please reduce, something like that it shows, right? There are some errors it is showing. Now, what we are supposed to do is like we have to ensure that all these errors need to be removed. So first, we will remove one or two errors from this. How we can remove this? We need to connect the clock. So first, we need to connect the clock, and then we have to connect the reset. How do we connect it when you say? Two ways. One is directly you can see here. There is a clock pin. Just there is a bubble. You can see that. Just click that. The moment you click that, automatically it connects the clock. Right? You're able to see that. Similarly, if I wanted to connect reset, I can just click reset. It will get automatically connected. So clock is also connected. Reset is also connected. Now, what is the next thing we need to do? There are some more errors. Okay, I will tell you how to solve them later. Not a big deal. Right. Now, the next thing is what? When you say we have to add some more components. I don't want only processor. If there is a master, then I want a slave, right? So I can use some memory. On-chip memory is my slave. So you can click this on-chip memory so that you can see that whether the tool is able to generate the RAM. You can see that on-chip memory, RAM or ROM. You can click that. This is the same RAM which we generated in the IP catalog, right? So you could see that. If you want a single clock operation, you can click single. If you want dual, then you can take dual port access. If you want, then you can click that. If you don't want, it is single port access. Okay. And now you can see initialize the memory content. If you say yes, then you have to provide .hcx file or .mif file. If you say I don't want, then you don't require to do that. And you need to provide the data width and the total memory size. For example, whichever data you want. If you wanted to have a memory size of 65536, whatever you want, you can provide that. Since we are creating a generic design, you don't worry about what would be the memory size. You can just say finish. Now you can see that there are some more errors that is done. One is it's showing that the clock also need to be connected here. So that means this clock needs to be connected and the reset needs to be connected. So we can connect that now. And what is the interface here? This is the master. Okay, NIAS is the master, and who is the slave? Is the memory is the slave. So what is the interface we use in Intel is the Avalon. Right? That is the interface, Avalon bus. So this slave need to be connected to the master. That is very, very important. So because your processor will have a data cache and instruction cache, you need to connect that to the slave. So connect them now here. Just click that, it will automatically get connected. Right? Now, once you connect it, you can see some more errors. What it is showing that there is overlap in the address. You can see that it is having the same address. So you don't need to do it manually. What we can do is like you can say system, right? And then say assign base address. Automatically it will assign the base address so that all the errors are removed. Okay. What are these two errors when you say? For the processor, NIAS, who is the memory? That's what it is. Who is the slave? It is asking. So who is the slave we kept in mind is the on-chip memory is our slave. It is our responsibility to provide, which could be acted as a slave. So that's what it is showing, that you need to provide who is the slave. Now what we can do is like go to the NIAS tool here, and you can go to the vectors here and say that who is the slave. It is showing none here. Now you select on-chip memory, and then here you select on-chip. Now you could see there are no errors. All errors are. Now you can close this. These parameters can be closed. Logically, you can get that logic. Now you could see the on-chip memory details are taken. Right? So this is the way how you can complete the principle. Right? Now you could see a specific thought process here. So if you want to add one more, for example, I want to add a JTAG UART. You want to add that? Yes, you can add it. For example, JTAG UART. I just wanted to add. Automatically it goes like finish. You can see there are 2 more errors. It shows that okay, these errors need to be removed. How do you remove this? Now you can connect this clock, and then you can connect this reset. This is the way how we can complete. Okay, so this is with respect to what when you say this is with respect to the NIAS to soft core processor, which is present inside the max10. So you can see this process. But then when we generate the same design for the Cyclone 5 device, we can try to do that with the HPS, which is the hard processor system. That could also be possible. Okay, let us try that also. The only difference here is like, instead of going to select NIAS2 processor, which is the soft core processor, we are going to choose the dual core ARM Cortex A9 processor, which is present inside the FPGA family. Okay, before that, let us explore some details about what is an SoC FPGA, and then I will show that demo to you. Let's minimize this logic. Let us understand what is the basic idea of the SoC FPGA. Okay, not this slide. Just a minute, I'll stop sharing for just a while. Sorry, I took the wrong PDF, so I need to close it and take from the source. Right. Now you can see what is an SoC FPGA. Right? What's the difference? Let us understand. Now, what is an SoC? Let us spend some time, and then I will stop with what is an SoC FPGA. Then we will go to the lantern. So, if you see here, what is an SoC? When you say an IC, designed by stitching together multiple standalone VLSI designs to provide full functionality for an application. If you see here in SoC, an ASIC vendor may use a library of code designed in-house, as well as some codes from fabless or chipless design houses, also known as intellectual property companies. That's what we did with IP now. What is the thought here when you say, what are the different applications of SoC? So there are so many applications, but then why these applications have chosen to understand that what is required in the SoC and what kind of basic applications which we do in our day-to-day life. One is cell phone. What is important here when you say should operate very low power? That is important. So the product and see the application which we wanted. What are the characteristics required? Second, telecommunications and the networking. What we wanted is we should handle huge data rate. Third one, when you say digital televisions and set-top boxes, what is required is we should perform real-time video and audio decoding functions. Fourth one, when we take television production equipment, then we should ensure that this requires extremely high computation rates. And then fifth one, when we take a video game, then we wanted that to happen that in the real time. The gaming action should happen in real time. Okay, so now all these things need to be done at the SoC design process. What happens here when you say, we wanted to choose the chip with required hard cores. We wanted to choose that with required soft cores, and then we should add the user logic. That is happening in the SoC design process. There, what is very important for us right now, earlier, FPGA was a separate, CPU was a separate, and DSP, the digital signal processing application, the processor, was a separate. What we wanted right now is like we need to reduce the cost, we should reduce the complexity, and then we should reduce the power. So all the three need to be reduced. How do we do that? When you say the CPU goes inside the FPGA and the digital signal processing block goes into the FPGA. Now CPU is also there, DSP is also there, and then you have all the IOs, everything put together. Now you can see that we have reduced the cost, we should reduce the complexity, and then we should reduce the power when it's there. How that could be possible? We call this term as a system on a programmable chip, where we call that as an SoC. What is the advantage of this when you say? The advantage is like earlier, you have FPGA separately and then CPU separately, but then now you have FPGA plus CPU, both are put together in a single chip. What is the advantage? Increase the system performance, reduce the power consumption, reduce the board size, and reduce the system cost. All could be possible, right? Number three, what is important at this junction is like, what is an SoC FPGA? ARM plus FPGA is equal to SoC FPGA. In SoC FPGA, what we are telling is, we have a dual core ARM Cortex A9 processor that is immersed inside the FPGA fabric. So ARM plus FPGA, we call that as an SoC. So we are getting the benefit of best of both worlds with this. Not only that, this is not only for the 28 nanometer FPGA, it is there for all the other high-end FPGAs. So in simple, how do we can understand it? ARM Cortex processor plus Intel FPGA is the SoC FPGA. So you have to see that, okay, that is available in the node device. That means you can see that it has a dual core ARM Cortex A9 that is immersed inside the FPGA. Now let us try this example with Cyclone 5 device and see how the same logic works. Okay, I'll close this. You can say save. Right, you can say, for example, not use this. You want to save, yes, you can. You can say generate. Now you can say generate. It will generate the logic. Now after generating, you can see that could be added into your Quartus file project. So you can add this. The entire system can be added. So say close here. Right, now what you can do, you can go to the Quartus Prime Design software, go to the files, right? Or you can also say like this, like go to the hierarchy and then you can say, and then you can say add project. So you can say the file here, which is available there, that you can add. You can see that, apply, then OK. Now if you come to the Quartus, you can see that the file is added. Just.qsys is there. Right, so this is same like how we did the IP, exactly similar. Right, now let us try the last example. We open the Quartus Prime Design software and we can go to the new project wizard again. You can also try that. So we can say here platform designer. Okay. And then you can say top. Say OK. Create it. Empty project. Okay. Now what you can do is like we can open the platform designer. So click the tool here. You can go to the platform design. Okay, so I have made a mistake here. So let us try with the Cyclone 5 device. So create it. So here you can say Cyclone 5 and say 5C SEMA5. So something like that. What is the dangerousness? Is like, is it an SoC or not? We are not very sure, right? So you can see that what is the problem we will face when we are not very sure whether that is an SoC FPGA or not. Okay. So let us go to the platform designer here. Okay, here, what you can do is like you can type here HPS. You can see here ARIA 5 or Cyclone 5 hard processor system. It is a dual core ARM Cortex A9, which is there, which is a hard processor system here. So you can click that. This would get generated. See here, this is a hard processor system. It is available. You can see HPS here, right? So HPS, when you say, this is called hard processor system. And you can also see that what need to be connected here. So you can see that how the clock need to be connected. All those information it is provided. You can just connect it, and then the other details we can discuss in detail in the tomorrow's SoC session. But now just we try to solve the problem. What is the error? You can see that. What are the things you should understand in this example is, here you can see H2F. That means it is HPS to FPGA. And if you say here F2H, that means it is FPGA to HPS. That's what we should understand. And then what we are going to use is the AXI, because earlier when we were doing with the NIAS2, we were using the Avalon. But then since we are going to use the ARM processor, we are going to use the AXI. Okay, advanced extensible interface. Now you could see I need to connect the clock, right? How do we connect this clock? You can see that F2H clock must be connected to a clock out. You can directly go here, F2H clock, just click it. Automatically that error will go. Similarly, what you can do is like you need to connect the H to F AXI clock that need to be connected. Just click that. F2H, that is FPGA to HPS. Click that. You need to connect that clock also. Last one, you need to connect the lightweight AXI clock. Also need to be connected. Just click that. You can see all the errors are removed. Now, if you want, you can generate this here. You can say generate. It will save. Just to say, just dot uses. Save. Okay, now you can say close. Right. Now what we can do is like we can add this QSys file to the Quartus project. So what we can do, you can exit it if you want, or you can say finish. Otherwise, what we can do is like we can come here and then we can add the file, right? So go to here and there is a test.qsys file, just to open it and say apply. This file would be added to your Quartus project. So here, if you go to the files, you can see that. Okay, so this is what we have seen, like how do we create with the soft core processor and how do we create with the hardcore processor. In tomorrow's lab, we will discuss in detail about how to create the embedded system design, and then there are specific lab manuals that would be shared, which you can do that with SoC. Today, I will share the timing lab manuals along with the basic SoC lab, which you can practice. And tomorrow's focus would be more on the embedded lab, which you could try that. Okay, so we will focus on an SoC lab where we will create a complete platform designer and then complete the project using the Intel SoC FPGAs. So I will walk you through this lab in detail tomorrow, and then you can practice this lab also. Where to download the source files, and how do we create the project, and how do we set up the hardware and the software. Everything I'll explain in detail for tomorrow's session, in the second session. So today you'll get us some idea about how do we create a project with the basic SoC lab. Tomorrow we will get into the details of it. Okay, I will share the slides, means the PDF, and then the lab manual, what we have discussed today. So please practice it before the tomorrow's class. So are there any questions, sir, which I can explain to them if there are any doubts? Thank you so much. If there are any questions, please let me know. It's like you have to definitely practice like what I do. You should also try that from your end so that you will get a better experience of how do we explore it, because there may be some kind of errors which you may get and I may not get. And by going through that errors, I can get some understanding of like what kind of debugging techniques that could be adopted, right? Sometimes my errors may be different and your errors may be different. Are there any questions, sir?
No question so far, sir.
All right, sir. Right.
So if there are any questions, participants can ask.
Yeah, we have around 10 minutes. If you have any questions, yes, definitely I can explain that to you. If not, I can share the details with you, the timing analysis lab manual, the intellectual property, the memory design lab manual, and the basic SoC lab. I can share that
Yes,
with you.
sir, along with the PDF of your presentations.
Yeah, sure, sure. I will share that today so that you can share it with them. They can practice it.
Yes, yes, sir. Yeah. It was really a wonderful session, sir.
Hello.
Yes, somebody is asking, sir.
Good afternoon, sir.
Good afternoon, sir.
Sir, I have one query that
Yeah.
we are going to design in Quartus by using IPs and platform designer. How
Correct.
we can verify these designs?
Right. So there are some different kind of debugging techniques. Like, see, we need to check, like generally, we have system console, and then we also have signal tap logic analyzer. And then there are different debug techniques with the ARM DSP also on the SoC side also. If you go through the Quartus itself, we could see those debugging. If possible, one or two debugging, I'll try to cover tomorrow. But you can get into the details here. You can see that as a system debug tool where you can see system control, which is a debug tool. And then we also have a signal tap logic analyzer. And then we also have in-system sources and probe editor. And then we also have an in-system memory content editor. So these things are available in Quartus. And then in the SoC side, we have an ARM DS5, which is Design Suite 5 compiler debugger, which is helpful for us to verify the SoCs also.
Okay, sir. Sir, my next question is,
Yeah.
we are learning this one Verilog and VHDL. So how system Verilog is useful over here?
All right, a good question. But here, the idea is like the system Verilog is an HDVL. It is a hardware description and verification language. So what happens is like when you are trying to do with HLS, right, high-level synthesis, you are converting a C or C++ code into an RTL. Or when you are taking a Simulink model and then converting into a system Verilog code. The advantage is all the C and C++ functions are available with system Verilog. Like whatever data types and operators which were not available in Verilog, they have it. So the high-level language conversion becomes very easier with system Verilog, and also creating a bus functional model, BFM, is very easy with system Verilog. So it is also useful for designers, but main intention is on the verification side.
Verification. Okay, sir. Thank you, sir.
Yeah, thank you.
Yes, thank you, Narendra. Any question from any other participant?
Hello, sir.
Yes.
Go in.
Sir, if we counter any error, then can we get help from the software here?
Yes, definitely. In the message console itself, it will show you that this is the
sir.
problem.
For solving the error.
Correct. So we also have an FPGA community, right? So for example,
Yes, I was talking.
Right. So we definitely have an FPGA community. We will definitely solve those issues. Like, see, general principle is like when there is an error in Quartus, right? It will definitely show you like what is the kind of error. It will show some numbers and other things, right? If you are not very sure, you can directly paste that in Google. It will take you to our FPGA community page where somebody would have encountered that error and how they solve it. You can see that. Definitely, it is possible.
Thank you, sir.
Yeah. Welcome.
Yes, thank you, Govin. Anyone want to ask any question? Otherwise, we can call it a day.
Hello, good afternoon, sir.
Yes,
Yeah,
good.
No, sir, regarding in this software, which is inbuilt programs, or we are going to write separate program to run that software, sir, which is available.
Yeah, Correct. So for this timing analysis and all, like we already have the design files which we can do.
Okay.
For the SoC program also, I'm going to tell you where we can download the reference files. So we don't need to create anything. All are available already. With the lab manual itself, we can go ahead with and guide the process. There is nothing we need to create from scratch.
Okay, sir. Sir, regarding application points, sir, may I know, sir, in mainly which areas it can be useful, sir, at presently, sir, this type of course.
So there is a specific SoC application session tomorrow, where how do we use the specific SoC FPGAs for IoT applications and for automotive applications. I will show that. There is a specific presentation. You will be getting fair idea about it tomorrow.
Okay, sir. Thank you, sir. Thank you, sir.
Yes, sir. Thank you.
Yeah, thank you so much, sir. I will share all the materials in another half an hour so that you can practice. You can send to them and let them practice it.
Yes, sure, sir. Sure. Thank you. Thank you, Padmanaban, sir. Thank you, all participants. So I am ending today's sessions here. So please join tomorrow also on time, just 5 minutes before 9:30. So tomorrow would be really very exciting sessions because the application point of view, we are going to see it. So thank you once again. Have a nice day.
Thank you, sir. Yeah. Thanks all. We'll meet tomorrow by 9:30 a.m.
Yeah.